Hello everyone, this is our session 1 on application of derivatives. Okay, so we've done one application of derivatives, that is the slope of a function, that is a slope of a tangent, sorry. So any function which represents a curve, okay, in an xy plane, when you take the derivative of that function, it gives you the slope of the tangent to that curve. We've done this as application of derivatives in the previous chapter. Okay, so let us revise that once again. So let us say that a function f of x, y is equal to f of x, okay, represents a curve. Any curve in an xy plane, right? So if it represents a curve, let us say you have an xy plane and you have a curve over here, okay, this is f of x, okay, y equal to f of x. Then the derivative of this function, that is dy by dx, equal to f dash of x, okay, at any point say x1 comma y1 on the curve, represents slope of the tangent to that curve. Tangent to the curve, okay, at point x1 y1. Okay, this we had done in the previous section. I'm doing it again. So this is any function representing a curve. If you take the derivative of the curve, then that derivative represents the slope. Okay, slope as in it represents the slope means equal to m, right? Now if it represents the slope of what? It represents the slope of a tangent to this curve. Okay, let us say that this is the tangent to the curve. 1 second, it should be touching the curve. Yes, so this is your tangent to the curve, and the point here is x1, y1. Then slope of this tangent is the derivative of the curve. Clear? So this is what is the first application. Now, if this is the slope of that curve, then how, of the tangent, then how do I write the equation of this tangent? So equation of the tangent will be given by y minus y1, right, equal to m into x minus x1. We have done these equations of lines previously. So any one form you can use. So I'm using y minus y1 is equal to m x minus x1. What is m? It is the slope of the function. So y minus y1 is dy by dx x minus x1. Clear? So this will give me the equation of the tangent to the curve. Okay, equation of tangent to the curve. Now, what about the normal to the curve? That means if the same tangent has a normal, let us say a perpendicular line, okay, this, yeah. So what is the slope of this perpendicular first, and what is the equation of this perpendicular over here? So let us find out that also. So we can say the normal to the tangent has a slope m dash, okay, it has a slope m dash, which is reciprocal of m, or you can say negative reciprocal of m. So let me write it in words only for you. So it will be negative reciprocal of m. What is m? it is the slope of the tangent. Okay, so how can we write the slope of the normal? M dash is equal to minus 1 upon dy by dx at the same point, that is x1 comma y1. Okay, and what will be the equation of this normal? So equation of normal is y minus y1 equal to m into m dash into x minus x1. So same way we write the equation, but our m dash, that is slope, will change. So equal to minus 1 upon dy by dx at x1 y1, right, into x minus x1. So we have to remember these two things, that is slope of tangent, this derivative of the function, okay, equation of the tangent, that is this over here, then slope of the normal, that is m dash minus 1 upon dy by dx x1 y1 at x1 y1, and equation of the normal, okay, perpendicular to the tangent. So it will be y minus y1 is equal to minus 1 upon dy by dx x1 y1, that is add x1 y1 multiplied by x minus x1. Okay, now this is the first application of derivatives, that is application in the geometric field, so geometry. Okay, this is the first one. The second one is derivative as a rate measure. So derivative as a rate measure. Now, what do we understand by rate measure? That means one quantity changing with respect to the other. When we say dy by dx, it means what? Y changing with respect to x. That means if x is moving by a small amount of distance, then y will also move by a small amount of distance. And what is that small amount? Dy and dx with respect to x, right? So derivative as a rate measure means what? One second. Yeah. So if we have y equal to f of x as our function, one second. Yeah. Y is equal to f of x as our function. Okay. If there is a small change of x1 to x2, that is x1 is changing to x2, then that small change is called as delta x. Okay. Now, how will y change then? Y is a function of x, right? So f of x1 will change to f of x2, right? Now, delta x is equal to x2 minus x1. Then delta y will be equal to what? That is small change in y will be f of x2, right? Minus f of x1. Okay. Now, if we take the quotient, that is if we divide delta y by delta y by delta x, then what do we get? F of x2 minus f of x1, okay, divided by x2 minus x1. Now, this can be called as slope of a secant of a curve, that is represented by f of x. So secant as in what? If this is f of x, right, then secant over here will be line joining 2 points, right? So delta y by delta x here can be called as secant, slope of the secant over here represented by say 2 points P and Q. P is x1 y1 and Q is x2 y2, right? Or you can say x1 f of x1 and x2 f of x. Yes, so delta y by delta x is the slope of the secant PQ, okay, given by f of x2 minus f of x1 upon x2 minus x1. Now, if we say that x2 is approaching x1, that is, the change is very minimal, very small, then delta x is called as a instantaneous change in x, which brings about an instantaneous change in y. Okay, that is y2 minus y1, or you can say fx2 minus fx1. Now, what do we understand when x2 approaches x1? It means that p and q are trying to be only one single point. That means we can say that limit of delta x is tending to 0. Okay, it's not 0, but it is tending to 0. So if I apply this limit on the function above, then I get limit delta x tending to 0, delta y by delta x is equal to limit delta x tending to 0, f of x2 minus f of x1, right, divided by x2 minus x1. Okay, so when we do this, or here you can say limit x2 tending to 0. Sorry, 1 second. Yeah, this will be limit x2 tending to x1. That is, x2 is approaching x1. So this side it will not be delta x. x2 approaching to x1. Okay, that is, it is becoming 1 point. So we have fx2 minus fx1 upon x2 minus x1. Now what is limit delta x tending to 0, delta y by delta x? It is dy by dx, right? dy by dx is equal to f dash of x, right? It is the derivative of f of x, f dash of x, given by fx2 minus fx1 upon x2 minus x1, right? So this is a basic definition of derivatives, dy by dx. So what have we come from? Secant to tangent. What is dy by dx? We just studied in the application as it is the slope of the tangent, right? So here from secant delta y by delta x, we've come to tangent dy by dx. Okay, so now we know two interpretations of f dash of x, that is dy by dx. What are these two interpretations? One, it is slope of tangent, okay, and second, you can say it is rate change, or you can say instantaneous change in x. Change in y with respect to x, or with respect to instantaneous change in x. So these are the two interpretations of dy by dx, okay, or you can say two applications in the field of geometry. Okay, we'll come across sums wherein we'll have to calculate small changes in values, okay, of one parameter with respect to other. That time this instantaneous change will become clear. Okay, like the topic that we did, rate of as a rate measure. Okay, now the third part in application of derivatives in geometry is velocity, acceleration, and jerk. Okay, so how can we use derivatives in velocity, acceleration, and jerk? Okay, this is a part of physics, you can say, which is included in maths, or you can say math used in physics. Okay, so how do we understand velocity with respect to derivatives? Let us say that we have a function s is equal to f of t, that is distance, showing distance of a particular place with respect to time. S is equal to f of t. Yeah, is the displacement function of a particle that moves along a straight line. Okay, now if I differentiate this, that is it's with respect to time, so we'll say differentiating with respect to time. So ds by dt is equal to f dash of t, right? Now, what is ds by dt in physics? We have come across this, that is displacement with respect to time. It is velocity. So velocity is f dash of t, right? First derivative of the function s equal to ft is v equal to f dash of t, velocity with respect to time. Okay. Now, this is velocity. Then how do we calculate speed? Speed is a scalar, right? So speed will be the absolute value of this derivative. So speed is equal to absolute value of this derivative that we have found out. So first derivative of a function, okay, displacement function. First derivative is velocity. Now let us derive, or you can say differentiate, the velocity function. So we have v equal to f dash of t. Let us do the differentiation of this function with respect to time. So dv by dt is equal to f double dash of t, or we can say s double dash of, just s double dash also can be written, or second derivative of s. Now what is dv by dt? It is velocity with respect to time is called as acceleration. So acceleration is f double dash of t, that is second derivative of displacement. Okay, so acceleration is second derivative of displacement. Again, if you have to, acceleration is a vector quantity, changes with respect to time. Now, if we further differentiate acceleration, that is differentiating acceleration with respect to time. Okay, so we are going to get dA by dt, okay, which is third derivative of our previous function, first function, third derivative of displacement. Okay, this is called as jerk. Now, jerk in itself, the meaning means, in Hindi it is called giving a jhatka, right? So, when you are on your bike and you accelerate, okay, if you are continuously changing your acceleration or increasing your acceleration, you are basically giving a jerk to the vehicle. So, acceleration changing with respect to time is the third derivative of your function, that is displacement. Okay, so here we did three terms: velocity, acceleration, and jerk from the first function, that is displacement function. So s is equal to f of t. Now from the first function s equal to f of t, that is displacement, we can get first derivative gives you velocity, second derivative gives you acceleration, and third derivative gives you jerk. Okay, so we can use this for sums wherein displacement is given and you just have to find velocity, you have to find acceleration, or acceleration is given and you have to find the velocity. This will help us to do that. So this is our third application of derivatives. In the next session, we will start with exercises based on these three applications that we have studied today. Okay. Now let us begin with numericals on the same. I'm starting with the exercise 2.1. Okay. Question 1 says find the equation of the tangent and the normal for the curves given below. All are of the similar type. I'll just solve two so that you know how to do them. I'm just taking the third one now. Question 1, third one. It says x cube minus root 3xy plus 2y square is equal to 5. You have to find the equation at the point given, root 3 comma 2. Okay, so what we do is, first step, we find the derivative of this equation that is given to us. So let us say differentiate with respect to x. So we have 3x square minus root 3 as it is, x dy by dx plus y into 1 plus 4y dy by dx equal to 0. Okay, we take all the dy by dx terms on the right side. So 3x square minus root 3y is left here equal to root 3x dy by dx minus 4y dy by dx. Let us get the equation for dy by dx. Therefore, dy by dx is equal to what we have on the left hand side, 3x square minus root 3y 3x square minus root 3y divided by, when we take dy by dx common on the right side, we get root 3x minus 4y. So root 3x minus 4y. Okay. Okay, 1 second. Okay, one mistake we've done here. We've taken x cube, should be x square instead of x cube. So let's just make this as x square. Sorry for this. Okay, this should be x square. So its derivative will become 2x. Okay. So we'll have 2x here. And in the equation, we'll have 2x minus root 3y and root 3x minus 4y. Okay, now this is dy by dx. Therefore, slope m of tangent is equal to 2x minus root 3y upon root 3x minus 4y. Okay, now this is slope of the tangent, right? So we can say that point root 3 comma 2 satisfies this slope equation. So substituting point 3 comma 2 in slope m. So how will we find the slope m? Substituting the value of x and y. So m is equal to root 2x, so 2 into root 3 minus root 3 into 2 divided by root 3x, so that is root 3 into root 3 minus 4y, that is minus 4 into 2. Now numerators cancel out, so we get 0. So m is 0. Slope is 0. That means what will be equation of tangent? Equation of tangent is equal to y minus y1 equal to x m into x minus x1. Okay, m is 0, so right side will become 0. Y minus y1 is equal to 0. And what is this y1? It is the point that they have given us. So y minus 2 equal to 0. x1 y1 is equal to root 3 comma 2. Okay, so y is equal to 2 is your equation of the tangent. So where all do we have to substitute the point that is given to us? One, we substituted to find the slope, and second, we substituted to find the equation. Okay, now m dash is equal to slope of normal. Okay, now how do we find slope of normal? It is minus 1 upon m, which is minus 1 upon 0. So 0 has no sign. We are going to get infinity here as the slope. So slope of normal is m dash, that is infinity. That means what will be the equation of normal then? Equation of normal is y minus y1 equal to 1 upon 0 x minus x1, right? We're substituting m dash also. So when I put 0 there, I get x minus x1 equal to 0. At root 3 comma 2, what will be our equation? X minus root 3 equal to 0. X is equal to root 3. Substituted only the x1 coordinate. This is your equation of the normal. Okay, this was question 1, the third one. I'm doing the 6th one just to get a hang of the trigonometric type. So we have x is equal to sine theta and y is equal to cos 2 theta. We have to find the equations at theta equal to pi by 6. Okay, so first of all, let us find the points x1, y1. We don't have that, so we can substitute theta equal to pi by 6 in x and y. So x1 is equal to sine of pi by 6 and y1 is equal to cos of 2 pi by 6. So what will be x1, y1 then? x1 comma y1 corresponds to sine pi by 6 is sine 30, that is half. Okay, and cos 2 pi by 6, that is cos 60, that is also half. So the 2 coordinates that we want are 1 by 2 and 1 by 2. Okay, so we already have x1, y1 now. Now let us differentiate. We'll have to use parametric differentiation. X is equal to sine theta, right? Therefore, dx by d theta is equal to cos theta. Y is equal to cos 2 theta. Therefore, dy by d theta is equal to minus sine 2 theta into 2. Okay. Therefore, dy by dx is equal to dy by d theta divided by dx by d theta. Correct? So, we'll have dy by dx equal to, what is dy by d theta? Minus 2 sine 2 theta, right? Divided by dx by d theta, that is cos theta. We can write this as minus 2 into 2 sine theta cos theta, right? Formula for sine 2 theta divided by cos theta. Cancels out. So we are getting minus 4 sine theta. This is slope m, right? dy by dx. Now m at theta equal to pi by 6 is equal to minus 4 sine pi by 6. So sine 30 is half. So minus 4 into half. Therefore, m is equal to minus 4 into half, that is minus 2. M is equal to minus 2. Therefore, equation of tangent will be, what will the tangent equation be now? Y minus y1 equal to m into x minus x1, right? So what is x1, y1? x1 comma y1 corresponds to half comma half. And m is equal to minus 2. Let us put these values in the equation. So we get y minus y1, that is y minus half, is equal to m. What is m? Minus 2 x minus half, right? So 2y minus 1 upon 2 is equal to minus 2 into 2x minus 1 upon 2. This will cancel on both sides. We'll have 2y minus 1 is equal to minus 4x, minus into minus plus 3. 2. Okay, so we have 4x plus 2y minus 1 minus 2 is minus 3 equal to 0. This is equation of your tangent. And how will we find equation of normal now? So m dash, right? So m dash is, let's say, equation of normal is equal to y minus y1 equal to m is minus 1 upon m x minus x1, okay, which will be y minus half equal to minus 1 upon minus 2 x minus half. This will become plus. Okay, we can send the 2 on the other side. So we have 2 into y, 2y minus 1 upon 2 equal to x, 2x minus 1 upon 2. This 2 cancels out. So we have 4y minus 2 equal to 2x minus 1. So what will be the equation? 2x minus 4y, right? 2x minus 4y minus 1 plus 2 is plus 1 plus 1 is equal to 0. This is equation of your normal. Correct? Yes. So this is how you find out the equation of normal and tangent. Okay. So if you here we complete